All right, so we are in an introduction to statistical learning, chapter 4, question 5 of the conceptual questions here. Um, so here's the question. It's a multi-parter, and so rather than front load all of the questions here, we'll just kind of tackle them as we go. So the first question is, well, it's right here, reproduced right here. So if the Bayes decision boundary is linear, do we expect linear discriminant analysis, or LDA, or quadratic discriminant analysis, QDA, to perform better on the training set? And then how about on the test set? Okay, so remember that the LDA and QDA are mechanisms for classifying observations according to data as either this type or that type. And with LDA, linear discriminant analysis, we assume, both LDA and QDA assume that that all of the categories are drawn from a normal distribution, and LDA assumes that the variance and covariance of all of the variables, the predictive variables that we're using to classify the observations, that they all have the same variance or covariance among them. And QDA estimates a different variance measure for each variable. Okay, so that makes QDA more flexible. And going back to chapters, I think 1 and 2 of the book, we know that more flexible methods will fit more complicated data sets, but at the risk of overfitting. If they are too flexible, they will begin to mistake noise in the data for signal, and then when it gets applied to a test set of data, it will mistakenly try to apply that false signal and tend to do worse on test sets. Okay, so that's really the answer here, but I think that we can go ahead and simulate this. So I have two variables here, x1 and x2. Okay, and x1 has a mean of -1. X2 has a mean of +1, and they both have the same standard deviation here. Okay, so I'm going to generate 10 observations from these variables. Okay, and so here I have created I've taken the theoretical distributions, okay, mean 1 or -1 and standard deviation 1, and I've drawn the theoretical curves. Okay, so the decision boundary right here is 0. This is where the two curves intersect. Okay. So now, if I were to just plot histograms of those two, I get this instead. Okay, because again, we don't have the theoretical distributions; we just have what we sampled. Okay, and if we look at these, and we also and here I also have the mean and standard deviation of the two, we notice that that the sampled data definitely has different standard deviations, even though they were drawn from distributions with the same standard deviation. The sampling bias is producing different variances or different standard deviations between the two of them. Okay, and so when we're going, now if we're just confronted with this data, we have to decide: do we think that the standard deviations of the two distributions are equal or not? Okay, and so for now we're going to assume that they are, because we know that they are. We set it up that way. Okay. Okay, so what we're going to do is we're going to split our 10 observations into a training set and a testing set. So we'll use 80% of the observations to make a training set, and then we'll use the remaining 20% for our test data. Okay, and so so I've already ran. Well, have I ran that? I don't know. So I'm going to run that. Okay. All of this must have recycled here while I was taking my time. So that's not a very pretty histogram. Try that again. Sorry about this. Just do it until I get a prettier histogram. That's a little bit better. Okay. So I've made my training set and my test set. And now I need to call the library mass. So if you haven't installed mass, you need to install mass as well. But I am going to run LDA, which is the command to run LDA, as well as QDA. And here class refers to whether the class is x1 or x2, and then the value is the value from those two distributions. Okay, so I'm going to run my LDA and my QDA, and now what I have here is so after I have fit to the training data with LDA and QDA, I'm then going to create predictions based on the test set for both LDA and QDA. And then I'm also calculating an error here. And there's a lot of different ways we can calculate error. And I am just defining it as the probability of a misclassification. Okay. And so when I run this, I get these two values right here, which is just basically the error that my LDA and QDA are making over the test set. Okay, and so a smaller error means that it's doing better on the test set, and so here we see that LDA is doing slightly better than the QDA. Okay, so that's nice. So I'm going to take all of the code that we have here and remove kind of the extraneous bits. So I can just run that whole process in one click. I can run everything. Okay. So again, we get the sum of the errors for LDA and QDA, and I can run this again and again and again and again. And if we do this a bunch of times, most of the time, as we'll see in a moment, LDA will perform a little better than QDA, but not always. So like for instance, on this run, we had that LDA did slightly worse, a slightly higher error than QDA. Okay, so so what we really want to do is we want to run this loop, or this set of code a lot of times. Okay, and that's what this is going to do here. So we're going to run that code m times, where here I've set m to 1,000. Okay, and so in fact I'll just run it, and we'll look at the output here in a second. Takes a second, sorry. Okay, all right, so so here's the output, and so I need to walk you through the output here. Okay, so this top number right here corresponds to this, and so this is the percent of times that LDA is doing better than QDA, right? After we run this code 1,000 times, 53% of the time LDA does better than QDA. Okay, now this number and this number represent, of those 1,000 runs, how much of the error was attributable to the LDA and how much of the error was attributable to the QDA, right? So if we sum all of the error of LDA and QDA, LDA represents about 49.96% of the error, and QDA represents about 50.04%. I mean, they're very, very close. And then here we have a histogram of the errors, okay, of the two models. And generally what you see is that the magenta, which corresponds to the QDA, is performing generally worse in most of these bins. Not always, but most of the time. Okay, so so there we go. Now, what happens if the variances differ? Remember, all of this was ran on the assumption that the two probability distributions for x1 and x2 had the same standard deviation, the same variance. Okay, so what if they differ? So we're just going to run this code again, this 1,000 repetition code, but now we have that one of the standard deviations is 0.75 and the other one is 1.25. Okay, so we're going to run this, and so now what we anticipate to be better is QDA, right? We expect QDA to do better both on the training set and the test set. Okay, the more flexible method will generally always do better on the training set. And we'll only do better on the test set if that additional flexibility is helpful or warranted. So, so in general, in this particular instance, we should expect QDA to do better in both the test set and the training set. Okay, so we're gonna run this 1,000 times with sample sizes of 10. Okay, so we run this. Okay. All right, so so again, we have the same outputs. Now we see that LDA does worse generally, so it only does as good or better than QDA 45% of the time, which means that QDA, right, is doing better most of the time here. And 50.6% of the error is attributed to the LDA versus QDA. Okay, so again, they're performing similarly, but now when we have different standard deviations for the two distributions, QDA is predictably doing better. All right, so now we are on part C. So in general, as sample size increases, do we expect prediction accuracy of QDA relative to LDA to improve, decline, or be unchanged? Okay. So in other words, we're going to run that simulation again, but instead of a sample size of 10, we're going to have a sample size of 15. And before we do that, we should expect that as sample size increases, we should expect the performance of LD. Well, okay, let me back up. I believe that this question is assuming a linear decision boundary, okay? In which case, LDA we should assume will do better. But as the sample size increases and increases and increases, we should expect the LDA and the QDA performance to converge. And the question is why? And the answer, I believe, is that as we have a greater and greater sample size, we get more accurate estimates of the standard deviations. Now remember, the standard deviations are equal in this particular data set, right? They're both standard deviation 1. Okay, and so that means as we get more and more accurate estimates of the standard deviations, we will notice that they converge, and then the performance of LDA and QDA therefore will converge because they will be estimating essentially the same thing. Okay, so we're going to run this. Let's see. Should really pause this while this is going. Okay, so we're here. All right. And so now again, what we get that the LDA performs slightly better, not much better. And then these are the percentages of the errors. Now, if we wanted to see how this did versus the smaller sample size, the sample size of 10, we would have to run this a few times and then run back up to here and run it a few times. And I've already done this, and generally what you will notice is that the percentage of times that the LDA does better is greater when we have a smaller sample size, and that's exactly what we would expect. Okay, all right. So finally, part D, true or false. Even if the Bayes decision boundary for a given problem is linear, we will probably achieve a superior test result or test error rate using QDA rather than LDA because QDA is flexible enough to model a linear decision boundary, justify your answer. Okay, so this is generally false, okay, because again, any additional flexibility that your model has the potential of mistaking noise in the sample data for signal. And then when it goes to predict on data that it has not been trained on, it will tend to apply that noise as signal that does not actually exist in the testing data, right? And so, in general, we would not expect what is being described here to be the case. So this statement is false. Okay, that's it.